Good morning, topology class. I hope you guys are doing well, staying healthy. I know you were on pins and needles wondering when the next lecture was going to come out, so here it is. We're going to look at some material from 3.3. We're nearly done for the semester, but I do want to talk a little bit about homeomorphisms. And this material will help us bridge the gap from what we've been doing versus some of the interesting things that we saw that day that we kind of looked at topology from a broader perspective. So homeomorphisms are really a key idea. So let's work our way up to that. So first off, let's let X and F and YR be two topological spaces. And then I want to pick a function from X to Y. So you guys got to play around with functions in the last homework. We say F is F to R continuous if, well, anytime you have an open set in Y, so U and R, that always implies that the preimage of U is in F. And just to be very clear here, I'm not assuming F is invertible. So this is the preimage of U under F. All right, and so sometimes if F and R are clear, we'll just say continuous. So you might be wondering, like, you've seen this word continuous before back in Calc 1. Yes, it is the same notion that you saw in Calculus 1, and if we have time at some point, I'll try and show you how our idea of continuity of a function from the reals to the reals ties in here. They certainly are the same. This is a more general notion that allows you to define continuity from different topological spaces, not just the standard topology on R. So let's look at an example. So here we go. We've got two little sets here. X and Y are nice and tiny. And I'm going to endow X with this topology F. Hopefully at this point, at a glance, you can see that's a topology. And then here's a topology R on Y. And so I want to go ahead and define a function F from X to Y. And I'm going to define it by, we're going to send 1 and 3 to A. And then we'll send 2 over here to C. And so the question is this function continuous? And remember, the way we're defining it, continuity, it has a direction. Is it F to R continuous, right? It's the same direction as F here. F is taking me from X to Y, and so I'm thinking of continuity in that direction. So is little f, big F to R continuous? And so let's see. So let's just work our way through. So we need to check the preimage of every set in R and see if it actually lands in F. So let's just begin. Let's look at the preimage under F. How about we start with the empty set? Well, the preimage of the empty set is the empty set, which is in F, so that's good, right? So we're picking things in R, and then we're checking if their preimage lives in F. And so the first set we checked was good. What about the preimage of Y? So this is equal to, if you want to write down the definition, this is all the stuff in X that F maps into the set Y. Well, that's everything. That's certainly all of X, which is, again, open, so we're good there. What about the preimage of the set? I don't know. Let's check the set BC. So I need all the things in X, each element of X, that F maps into the set BC. So all the things in F that F sends to either B or to C. Well, F sends nothing to B, but it does send 2 to C. And so the preimage of BC is just the set 2, which is, again, in F, right? 2 is in F, so this is certainly open. And now let's check the last set. Hopefully we'll have continuity in a minute. So the preimage of the set A, well, let's see. We can see F sends 1 to A and 3 to A, so this is the set 1, 3. Oh no, sadly 1, 3 is not in F, so we'll put a big X there. And so now we can say, thus, F is not F to R continuous. So that's the idea Let's keep the same example, but we'll define a different function. So same setup. I'm going to slightly change our function. We're going to go g from x to y. So same order. We're going from x to y. And I'm going to send everything in x to a. So 1, 2, and 3 all go to a. And so is g f to r continuous? Well, let's again check everything. I'll go a little bit quick here. So the preimage of the empty set is again the empty set. We're good. The preimage of y is again x. We're good there. And now let's check the preimage of the set BC. Whoops, I've got my symbols backwards here. It should be parenthesis, squiggly, BC. Well, if you notice, G doesn't send anything to BC, so this is just the empty set, which is actually good news. And then the preimage of the set, whoops, the preimage of the set A, that's everything in x, that's just x, so we're good to go there. And so we can say thus G is f to r, struggling to write today, f to r continuous. So that's the big idea. I wish so very much that I could hear all your questions right now, but I can't. I'm not going to prove this theorem. I would encourage you to read through the book and look at it. But I do want to state it because somehow it's intuitive and we're going to want to know this. Anytime you have the composition of two continuous functions, it remains continuous. And now to write that down, what precisely this means, you're going to need to set up the topological spaces A. You've got sets A, B, C. You need a space, at each point. And anyway, I would encourage you to at least write down the symbols. What is this actually saying? And you can open up your book and look at it. But I'm just going to mention it as a passing fact so that we're aware of that. You can prove this if you want to, something to do. Some of you guys need things to do, I'm sure. It's not like you're busy or anything. It's not like the weather's nice or anything like that. So you can certainly prove that yourself. Let's break this video here, and then we're going to look at another example in the next video.